Okay, your 10s, good afternoon. Sorry I can't be with you today, but I'm on a course which is run from the UK and it only goes at very awkward times. So there it is. What we're thinking about today is this thing called resultant forces. Now, basically, what we're going to do is we're going to think about the forces on an object and what they might do to it. You can see my wonderful artworks today that I've prepped ever so carefully. What we've got here, just so you're clear, this is a car. And we're going to think about the forces that might actually be on it. Generally, in GCSE science, we think about a car that's just on a nice, flat, straight road. We're going to keep things fairly simple because complication can creep up quite a lot in this. Anyway, what we might think is, well, what would a forward force on a car be? Well, that would be the actual engine force. You might call it a thrust force from the engine. Okay, usually conducted from the wheels, but I'm going to just draw it here. Now, what could the backward forces be? Well, we think about what forces act against that. So as the engine pulls the car, or pushes it, whatever, push or pull, any forces of push or pull, makes the car go forward, there's going to be something which acts against that. And there's two main ones we'll think about. So there is this, which we're going to call is the air resistance. I'm just going to simplify that, AR. And there's also frictional forces, mainly between the wheels and the road. So I'm going to call that F. And we think, all right, so let's then consider what happens if we suddenly turn the engine off. So, or we just take our foot off the gas. So get rid of that. Boom. Now, the car isn't instantly going to stop. That doesn't happen unless we run into a wall. And even then, it's not actually instant. It does take a small amount of time. But the car is going to slow down. So what it's going to experience is negative acceleration. Or in this case, we could say backwards acceleration. It's going to slow down, basically. We've just taken a very physics way of saying it's going to slow down, backwards acceleration. What though if we consider whether we step on the gas? So we step on the gas. Here we are driving normally. Let's just imagine that the air resistance and the friction is equal to, we'll just call it thrust, the thrust force in the engine. Well, that means the car is not going to accelerate. It's not going to get faster or slower. It's going to continue doing what it's doing. No acceleration when the air resistance and the friction are equal to the thrust force in the engine. So what then if we suddenly increase the thrust force? Get my eraser here. So let's just draw a larger arrow for that. Yep. Okay, so let's just make that a really big arrow. Okay, so air resistance plus the friction is less than the thrust. What must happen? It's going to accelerate. It's going to accelerate forwards. So resultant forces, there's what we're talking about. Other example here, we think maybe about a cyclist on a bicycle. Now, I've drawn this because I want to draw attention to the fact that we very rarely actually draw these things. It's way too much hassle. We're not here as artists. What we will often do is we'll simplify an object. We'll think about this bicycle, and instead of drawing a bicycle every single time, we will just draw a box or sometimes a circle to represent the object. And then we think about the forces on that. So we might think, for example, about this guy that's not moving at the beginning, but then he applies a pedaling force. At the very beginning, if you're not moving, the friction and the air resistance are going to be really small. It's supposed to be an F. This iPad keeps correcting me. So we know is that the pedaling force is greater than the friction and air resistance, which means our guy's going to accelerate forwards. So there's a useful thing. We're going to get into the details of that a little bit later. What we're going to first of all think about is how do we just resolve our resultant forces. So let's just give some numbers to these because we do use numbers, and we're going to include some direction in this as well. So let's just say that our pedal force is 20. Do you remember the unit for force? Going to give you a bit of thinking time. Don't need to say it. Hopefully it exists in your minds. It is 20 newtons. And let's just say our friction is 0.2 newtons and our air resistance is 0.8 newtons. I know these arrows are obviously very much not to scale, but there it is. So that means the total force is 20 minus the sum of these two, 0.2 plus 0.8. Now, why am I adding these two together? Well, they're both working in the same direction. And why am I subtracting these from this one? Because they're working in opposite directions. So hopefully, probably most of you already know what the solution to this is. We're really just saying 20, go away, minus 1, which is equal to 19 newtons. But because we're thinking about something which must include direction, we're thinking about, do you remember what we call something that includes direction? Is a vector quantity. We must include the direction. So that's 19 newtons to the left. Or what you might also do instead is you might just write 19 newtons with a little arrow across the top of it. Boom, there we go. So I'm going to show you some examples which are very similar to questions I'm going to give you in the worksheet. But here is a simple definition of a resultant force. So the resultant force is the sum total of all the forces on an object, considering their size and direction, just as we said before. So the size of this force here is 20 newtons to the left. The size of these two is 1 newton to the right. And there we go. We just find the sum total. They work against them. Okay, think about Alice, the box here, or Alice, the person, whatever it is. Notice that the arrow on the left is bigger, so we'll just, usually they'll often be the scale, but we'll say it's 50 newtons, and then it seems reasonable to call this about 40 newtons. And there you see, okay, 50 going left, 40 going right, so the total is 10 newtons to the left. Or you could just say left. Not a huge problem if you do both. There's no problem in doing both things. Think about Bob. Now, we'll think about here is a force. What we'll say is 1.2 kN. Thinking for a second about what that K actually means. And let's just say that this is 650 N. And this one is 700 N. Remember, we must be working the same units. 1.2 kN is the same as 1,200 newtons. And then what I'm going to do is, because these other forces are working in the opposite direction, 650 plus 700. Well, okay, that means we're dealing with 1,200 minus 1,350, which means we're getting minus 150. Or we could, in this case, say, that tells me it's working this way. So we could just say 150 newtons to the right, just like that. On to Charles here. So let's just say that this is 80 newtons and this is 80 newtons. Hopefully you realize straight away that these two, they're exactly equal. So they're not going to have an overall effect on it. So the total of these two blue ones is going to be 0. But what we've got is two forces working against each other up and down. So we'll say, I don't know, this is 70 newtons and this upper one is 50 newtons. So hopefully you've realized this. It is just 20 newtons down. Okay. Now we're going to think about the example of a person. We're going to think about the forces of this guy that's just standing right here. And what I'm going to do, it may be obvious why I'm not going to draw arrows in this person, because it's going to look very weird if I do. So there is an example of his gravitational force, or hers. That is their weight acting from their center of gravity. And let's just say typical person, okay, we'll just say that their weight, 70 kilos times 10, is 700 newtons. Now, imagine this is you, and imagine the only force is downwards. What would happen is actually you would splat into the ground, because you would all be accelerating, every part of you would be accelerating downwards. Okay, there's got to be something back from that. And so what we get is, because this person is not accelerating, what we have is their normal contact force. It just means the force which is happening through your body due to the strength of your body as it interacts with the ground. And if you're not accelerating, that means that these two forces must be equal. So 700 newtons is your normal contact force. So when you're standing still on the ground, the normal contact force is exactly equal to the force of your weight. Now, why am I talking about that? Because we need to consider what's going on when something's not accelerating. The resultant force on this person is equal to 0, which means no acceleration. So, here's the thing. If you take nothing else away from this, you need to remember that an object will accelerate in the direction of the resultant force. And if there is no resultant force, then they simply will not accelerate. That means they might continue at the same speed and direction. That's the same. That is not accelerating if you're moving at the same speed and direction. What we're going to think about here is, I've done the drawing because I want to emphasize and talk about a bicycle. But let's just say this guy starts off. So he's going to start off, and there's going to be, we'll just call that the pedaling force. And the friction and air resistance will be very small. So we'll just call those F and AR. Okay, so the pedaling is much more, very much more than friction and air resistance added together. So what does that mean? It means he accelerates in the direction of his resultant force. So we can say accelerates left. Now let's consider a moment later. He's probably going to have more or less the same pedaling force. It does vary slightly, but we'll say that he's not going absolutely nuts on this. Now, as you start moving, your friction and your air resistance both increase. Now let's just say then, okay, the pedaling force is equal to friction plus air resistance once you're moving at a certain speed. Now what that means is there's no acceleration, and you will just continue moving at the same speed. You can't get any faster without suddenly increasing your pedaling force. You'd have to, right? So, if you imagine just riding gently along the bicycle at a constant speed, if you want to go faster, you've got to increase your pedaling force. You want to go faster again, you've got to increase your pedaling force until you get exhausted. That's something about, okay, he stops pedaling. So you stop pedaling, just like I said in the example of the car before. If you stop pedaling or you take your foot off the gas, you don't instantaneously stop. That would be really disastrous. But the friction and air resistance still exist. They are still both there. So the friction and air resistance are there. So that means in this case, the resultant force, let's say res 4, is equal to friction plus air resistance. And that is backwards, which means he is accelerating backwards. Or you've got negative acceleration and he is slowing down. I just said the word acceleration, which made me write the word acceleration. Accelerates backwards, which means slowing down in this case. A more usual way of saying it. So, those are the main things you need to consider for this lesson. I will put these notes up on the Google Classroom along with the video so you can scan through this. I think I found a way to put these onto PDF. Okay, but main things are, the resultant force is the sum total of all the forces on an object considering their size and direction, and an object will accelerate in the direction of its resultant force. Thank you.